Okay, so we've spent some time graphing, and now we need to look a little more closely at these equations and come up with how to solve them. So the two main points that we're going to look at are, one, obviously we've spent time graphing, so we will graph them, and solving them using square roots. Square roots being the simplest form of solving that we have, provided that the conditions are right. So to understand how graphing is possibly one of our solving methods, it's shown up as a solving method for almost everything that we've seen. And, what are we looking for when we look at these graphs? Well, that comes down to us understanding the way that solutions get talked about. Solutions are known by a couple of other names. They're sometimes called roots of the equation, zeros of the function, or the one that's going to be most useful to us with graphing, they're the x-intercepts of the graph. Those are things we can find, those are things we've talked about. Now that means that we also have three scenarios for solutions. You could have no x-intercepts, which means no solutions. You could have just your vertex on the x-axis, so one solution. Or you could have a pretty standard looking, crosses the axis twice, two solution quadratic equation. So let's take a look at one. If we want to solve x squared minus 4 is equal to 0, well, the first thing we need to do is make sure that we're actually looking at it set equal to 0. If it's not that way, we need to move pieces around. We need to make it that way, which in reality means that we want to look at it as close to being standard form as possible. Now, what do? How do we generate the graph? Well, x squared minus 4 equals 0 only has one variable. We need to write it with 2 if we're going to look at a graph. So we graph what we call the related function. Now, the related function for this equation is y equals x squared minus 4. Now, from everything we've looked at with graphing, we know that x squared minus 4 is nothing more than the parent curve moved down 4 spaces. So if we take a second, we plot that vertex, we use the shape of the parent curve to find some other points, we use the axis of symmetry to reflect those points, ultimately we get this curve. Now, we said before, we're looking for the x-intercepts. There happen to be two. There's one at negative 2, 0. There's one at 2, 0. If solutions and x-intercepts are actually the same thing, then it's the x values within those ordered pairs that constitute our solutions. So the solutions of x squared minus 4 equals 0 are x equals negative 2 or 2. What if I give you this graph? We're looking to solve the equation x squared minus x equals 6. Now, written as the related function, we'd put it in standard form, x squared minus x minus 6 is equal to y. There's the graph. Take a moment right now, and I want you to find the solutions to that equation. Hopefully we just found ourselves those two x-intercepts. There's one at negative 2, 0, there's one at 3, 0, which means the solutions to that equation are x equals 3 or x equals negative 2. Now, this is all well and good, but we all know that graphing is inefficient. Graphing is not always accurate. Graphing is tedious. So when the graph is given, great, I can look at the graph, I can find the intercepts. I'm probably not going to choose graphing as a method. I'm going to want an algebraic means of getting this done. The first one I'm going to talk about is going to be square roots. Now, square roots come with a set of restrictions. We need to only have one place where x exists in our equation, which means that if I write my equation in standard form, I want that b value to be 0. If that b value is 0, well, then I could use square roots. If it's not, I've either got some manipulation ahead of me, or I'll choose another method to be talked about later. If we look back at that first example, written in standard form, set equal to 0, x squared minus 4 equals 0. Notice that the b value doesn't exist. It's 0. So in this case, square roots would be a good choice. The second example, Well, when that one was written in standard form, it had a b value that wasn't 0. It had b equal to -1. In this case, there's x in two places. That's not good for us in terms of square roots. We won't choose to go that route. So how do we get it done once we make the decision to solve? First things first, we need to isolate x squared. Once that's done, we're going to take the square root of both sides, essentially undoing the square. Now, things to keep in mind. The square root of a number technically has two values. The square root of 4, well, it says what number times itself is 4. Technically, both +2 and -2 fit that description. So we need to accommodate that by saying plus or minus, whatever we end up with. And then we'll isolate x. So taking that first example, x squared minus 4 equals 0. I'll isolate x squared. I'll take square roots of both sides. The square root of 4 is both plus or minus 2. And then make a statement about my solutions. X equals 2 or x equals -2, taking that plus or minus option into account. Another one to look at. We're going to be 2 steps to isolating x squared here. We're going to have to both add 9 and then divide by 4. X squared equals 9 over 4. We shouldn't be scared off by a fraction. We can take a square root of anything we want as long as it's not a negative number. So x squared equals 9 over 4. We'll take the square root of both sides. The square root of 9 is 3. The square root of 4 is 2. I get x equals plus or minus 3 over 2. So x is 3 over 2, or x equals -3 over 2. Final example. X minus 5, the quantity squared, minus 36 equals 0. Now this one looks a lot closer to vertex form. When we see things in vertex form, we can still use square roots. We have to make a subtle adjustment to our steps. That first step gets the caveat of we could actually isolate that entire x plus or minus h squared term and take a square root. So I'll just add 36 to both sides. Take a square root. X minus 5 equals plus or minus 6. This is where that fourth step really makes a difference. I need to write both versions of this equation. X minus 5 equals +6 or x minus 5 equals -6 and solve for x within those two little mini equations. Ultimately, I arrive at x equals 11 or x equals -1.